In the last few lectures, we have been looking at various phases of embedded systems design. We started with the situation in which the embedded systems designer had just a hazy and rough idea of the embedded application that he wants to design. Then he jots down this idea in English as accurately as possible, specifying the inputs to his system, embedded computing system, the expected outputs from the system, and describing as accurately as possible the functionality of his embedded system, the behavior of his embedded system, how the embedded computing system transforms the input into outputs. He writes that in English. Now, given this English language description, the designer embarks onto the stage of formal modeling of this behavior using tools such as the sequential program modeling languages and then the tools such as the hierarchical and concurrent finite state machines, the program state machines, etc. And after this, he has a model, formal models describing his entire embedded systems behavior, with possibly specifications also for performance constraints such as latency between two components, maybe area related constraints, power related constraints, etc. We also saw that there are a few modeling strategies such as discrete event systems, which allow direct synthesis of the controller, taking into account the platform constraints as well. However, during that design we also told that for very complex embedded systems, such accurate modeling of the behavior of both resources, the specification and the system, it may not be possible. Okay. For those such complex embedded systems, when such accurate modeling so that synthesis can be done directly is not possible, we obtain from the model task graph like structures. From the program state machine model, say we obtain structures like that, a task graph corresponding to the embedded computing system that we want to design. Given such a task graph like structure, we then embark onto the stage of hardware software partitioning, in which we decide which of the task nodes in this task graph will be executed on general purpose processors, say using a C language, high level C language, and compiling it into its corresponding machine language or other high level languages, and also which task will be designed in hardware. Okay. Hardware, which essentially means that for that functionality we will build a single purpose processor, a digital circuit which will be finally fabricated onto fabricated as a chip, or many such functionalities combining together will be formed into a chip and placed onto the embedded system on the embedded system with other components. There, at this stage, we could also decide other implementation platforms, such as we can have, instead of having these extremes of completely a general purpose processor or a completely customized hardware, we can have other implementation platforms as well, such as specialized processors such as digital signal processors, DSPs, ASIPs, application specific integrated instruction set processors. So, application specific instruction set processors, ASIPs, or even say SIMD processors, single instruction multiple data stream processors, and FPGAs, field programmable gate arrays, various other computing platforms with various degrees of flexibility and performance performance that it provides can be chosen as our desired implementation platform for a given functionality, and those functionality described as tasks in the task graph. Then we saw how the architectural design of the hardware can be obtained. Okay. So, from the functionality described in say a high level Verilog or VHDL code, we saw steps which provides you we have shown steps which ultimately derives the data path and the control path for the hardware that we want to design. Of course, there are subsequent phases before we can actually realize a packaged chip, and we have discussed those phases, but we have not gone into those phases. For example, we saw that there will be logic design, then circuit design, then physical design, fabrication, packaging, etc. Okay. And those will be more a part of CAD for VLSI design course and not an embedded systems course, and we have not shown that. After we have understood, got an overview as to how hardware is designed, we will now have to embark on system level analysis and design. So, after we have designed, we will have a system in which different tasks in the task graph will be executed on general purpose processors, on specialized co-processors, on specialized digital signal processors, or we will have customized hardware such as subsystem A and subsystem B, and different tasks will be implemented on different such subsystems, hardwares and softwares. And each of these components, be it general purpose processors, specialized processors or customized hardware, all these things need to be able to talk together, talk among each other, because the tasks need to communicate information among each other, and this happens by means of an interconnection network. Such interconnection networks could be buses, could be a shared bus. And hence, if it is a shared bus and multiple tasks are communicating among themselves, the shared bus needs to be appropriately scheduled, so that there can be smooth, seamless communication between tasks. Similarly, if multiple tasks share the same implementation platform such as a general purpose processor, we need to schedule the tasks onto them. If we have multiple such general purpose processors, let us say platforms, which on which multiple tasks are scheduled, we need to be able to do multi-processor scheduling as well. And we saw that there are many issues to consider when we consider a system, and how performance will be satisfied, whether performance will be satisfied by implementing this embedded system on this given implementation platform with multiple components. Suppose this embedded system does some big computation as a stream. Okay, it takes input at the rate of n samples per second, does a lot of computation through these components, through all these components that we have here, and produces data every 1 by n seconds. So, sorry, what I wanted to mean is that, let us say the data comes at the rate of every 1 by n seconds, and then the output also has to be provided at the rate of 1 by n seconds. So, in real time embedded systems, validation of performance. So, what we want to do here, we want to validate whether the performance requirements that are stipulated for my embedded system will be met if I implement it onto such a platform, implementing some components in hardware, some components in software, connecting it with such an interconnection network, okay, applying certain scheduling principles on the buses and the processors. If I do all these things, will I be able to meet the required performance that my embedded system needs to meet? That is what we need to validate. Okay. So, with respect to embedded systems, validation is almost always linked to satisfying constraints on time. So, we will see this how this important constraint can be met. For example, let us say this embedded system is a control system which acquires data at the rate of n samples per second, and then we need to validate whether this can we ensure that each data item will be processed in less than 1 by n seconds. So, what will happen if we are always able to process this data within less than 1 by n seconds, and if we can certify that it will never take more than 1 by n seconds, we will not require buffers to store unprocessed data. Okay. If we cannot ensure that, we will require some finite sized buffer to store unprocessed data. Suppose this embedded system, the time taken is not always fixed. It is around 1 by n seconds on an average, or a bit less than 1 by n seconds on an average, but sometimes the time required to process the input data could be large. So, therefore, it may not always be the case that the data will be processed within less than 1 by n seconds. Hence, we need buffers to store for the situations in which there are data items which could not be processed, because input samples will always be coming at 1 by n seconds. Now, therefore, what we want to stress here is that we need to correctly analyze what will be the time taken by the embedded system to process each component in data. What is the upper bound on the time that will be required by this embedded system to process each data component. And what we will see is that it is not very easy to do so, to obtain such estimates. Why are obtaining such end-to-end estimates not that easy? Because analysis of timing behavior must be done in the face of microarchitectural intricacies. For example, what is the pipeline structure? How many pipelines do we, if I do not have a pipeline structure, each data component may need, say, k time units. If I have a pipeline structure, finally, I may require only 1 time unit on average to process each data component, for example. We have to take care of the resource contention among programs running on the same processing element. That will be done through uniprocessor scheduling. We saw that there are multiple tasks onto the same processing element, and when will each task execute such that both tasks will be able to produce their outputs within given deadlines, that has to be correctly analyzed and scheduled, and that will be done via uniprocessor scheduling. We will see uniprocessor scheduling principles in the future classes, starting possibly from the next class. And we will also see that there can be resource contention among multiple programs running on different processing elements. Let us say if this embedded system would have multiple general purpose processors onto which a set of n tasks have to be scheduled on a set of m processors. How do we do that seamlessly, so that deadlines of all the task instances, all instances of all tasks will be met? So, we said that each of these tasks will be fed data at a rate of some samples, and each instance for which this code runs will be called a job or an instance, and the task is this series of instances over which it receives data and produces output. So, there could be contention due to other shared resources like last level caches. So, we can have last level shared caches, and when one task executes on a processor, other task data may be flushed, and therefore, when the other tasks comes back to the processor, it will not find the data in cache, and it may incur a lot of cache misses, and hence the time taken could be large. So, the time depending on cache misses could vary a lot. The time taken by a task to complete can vary a lot depending on whether there were cache misses. Okay. Similarly, there could also be the case depending on whether there were a lot of page faults or not, the time taken by a certain task can vary. The overall time taken could also vary depending on the computation times over the bus or the interconnection network. As I told that these tasks, multiple tasks this is a task graph structure, where tasks communicate data output of one task goes to the input of another task. So, I have task graph like structures like right. So, I have structures like this, and the output from one task, say T1, T2, T3 and T4. So, output of T1 goes to two outputs from T1 goes to T2 and T3, and therefore, such dependencies. So, if T1 is implemented on say the CPU and say T2 is implemented on say the subsystem, I need to be able to communicate the output of T1 to T2 through this communication network or through this bus, and there will be multiple tasks which will be communicating their data through the bus to other tasks in other components, and this has to be seamlessly done. To do this seamlessly over the shared communication medium, the shared bus which is shared by multiple tasks, multiple components, you need to be able to properly schedule the bus. We will see bus scheduling strategies as well. time time taken by the system could also depend on asynchronously coming input interrupts from peripheral devices. Other peripheral devices interrupt, and therefore, the tasks may have to wait until such interrupts are serviced, and the overall time taken by the system could vary a lot depending on whether interrupts from peripheral devices were received. Okay. So, these were just a few issues to show that the time taken, it is very difficult to tightly estimate what will be the time taken by an embedded system. However, tighter estimates do help us get estimates of how much resource that will be required, and hence we will not waste resources, because otherwise we have to keep a lot of resource thinking just of the worst case time that might be taken, and hence the design will not be that streamlined, would not be that cost effective. Hence, tight estimate of the time taken is required, and therefore, we do that. So, we just understood that a tight analysis is extremely complex. Execution time of even a single instruction may vary depending on microarchitectural features, as I told you. What could be the different microarchitectural features? For example, whether there was a hit or miss on the instruction cache, whether its operands are a hit or miss on the data cache, whether it faces pipeline stalls due to data dependencies or resource constraints from other instructions. So, whether do we have data hazards, read after write, for example. Okay. Such if we have such data hazards, then we have to face pipeline stalls, and time required could be more. Whether branch prediction was correct or wrong. So, depending on whether a branch at a particular point was predicted correctly, the time taken, because if the branch prediction is correct, it already executes a few instructions within the branch, within the predicted branch. If it is wrong, all those instructions have to be flushed, and the other branch has to be taken. So, we save time if the prediction is correct. On the other hand, the time required could be more if branch prediction is wrong. Now, it is not only we told that it depends on the time required by the tasks and the scheduling within the processor, but it is also equally important about what is the time taken on the bus. We told that, but we will see that with an example that why system level analysis of both the tasks as well as the bus scheduling has to be taken into account. If not done correctly, there could be anomalies, and through this example we will see that. Let us say that we have 4 processes, and let us say these processes are 4 processes in an automotive system, such as the anti-lock braking system, the cruise control system, and let us say the fuel injection system, and let us say the brake controller. Okay. These are 4 processors, and we also suppose that these 4 processors, for the sake of simplicity, that these 4 processors are running on separate processing elements or processors. So each process is in a separate processor. However, these 4 processing elements are connected by a single shared bus, and we also have a very simple scheduling strategy for the bus. We say that whenever you have multiple bus messages to send through the bus, how do you decide which message can be sent through the bus? Multiple messages from multiple processors are there to be sent through the bus. How do you decide which message will be sent through the bus? It will be decided through this simple bus access priority, let us say, where priority of the processing element or process P1 is highest, followed by processing element P2, followed by processing element P3, and followed by processing element P4. So, P4 has the least priority to get the bus, and P1 has the highest priority to get the bus. And also, for the sake of simplicity, we assume that all message transmissions only take 1 unit time. So, just one piece of data which takes 1 unit of time, we consider that. And each task is marked. So, these are the tasks C1. So, these are the processing elements P1 and the processes actually are C1, C2 and C3 and C4. These are the processing elements. So, these are the processes or the tasks. So, C1 is one task, C2 is another task, C3 is another task, C4 is the other task. So, C1 is mapped onto processing element P1, C2 is mapped onto processing element P4, C3 is mapped onto processing element P2 and C4 is mapped onto processing element P3. Okay. And with beside each task C1, C2, C3, C4, we have kept the lower bound on execution time and upper bound on execution time. Let us say we have somehow come to know what will be the overall data that overall the possible data which C1 can take as input through its arguments or through from outside. The different control paths that it follows, for example, this task is C1, overall such control paths, overall such data, the least execution time that it takes is 3 units and the highest execution time that it can take is 4 units. So, overall data that it can ever receive, C1 takes 3 unit of time at least and 4 unit of time at most. For all other computations or tasks, we have kept the lower bound on execution time and upper bound on execution time to be same. For all other tasks, the lower bound and upper bound is same. And we say that after C1 completes its execution, message M1 from C1 goes to C3. Similarly, message M2 from C2 goes to C4. And C3 and after receiving message M1, C3 can execute. After receiving message M2, C4 can execute. After C4 does its execution, C4 sends message M3 to processing element P2, which is possibly processing element P2, and then this process, this computation component ends. Now, let us consider two cases. One in which the task 1 C1 takes 3 units of time and the other case in which task 1 that is C1 takes 4 units of time. So, when task 1 takes 3 units, so this is the case in which task 1 takes 3 units of time. This is the progression of time. On the x axis we have progression of time. These are the 4 processing elements and this is the bus. This one is the bus, these ones are the 4 processing elements. So, when C1 takes 3 units of time, the computation on P1 task T1 executes in the interval 0 to 3 and completes at time 3. C2 on the other hand executes in parallel on P4 and it also takes 3 units of time and completes at time 3. It takes 0 to 3. Now, at time 3 both messages M1 and M2 are ready and they are sent one after another. So, let us say because M1 and M2 are ready and both are ready, and because M1 has a higher priority, M1 is from P1 processing element P1 and therefore, M1 has higher priority than M2 which is on processing element P4. So, although both are ready at 3, M1 sends its message first between 3 and 4 and then M2 sends its message between time at 4 and between 4 and 5. At this slot M2 sends its message before M1. And after M1 sends its message, C3 starts at time 4 itself. At time 4, C3 starts at time 4 and as we are seeing C3 takes only 1 unit of time. So, therefore, at time 5 C3 completes. At time 5 C3 completes and M2 also arrives at processing element P3 at time 5. So, now C4 can start. C4 starts at time interval at time 5 and it requires 2 units of time, and therefore, it ends at time 7. After C4 completes, the final message M3, that is the output, can be sent at time 7. So, at time 7, after C4 completes, the message M3 can be transmitted. So, total time to end this whole computation process is 8 time units from 0 to 8, from 0 to 8. Now, when C1 takes 4 time units to execute, so it is more. So, in the first case C1 takes 3 time units to execute. Now, in the second case C1 takes more time to execute. Now, so both tasks on P1 C1 takes 4 time units and completes at time 4, and on P4 C2 however takes only 3 time units, because its upper bound and lower bound are both 3 time units, and it executes on P4 and completes at time 3. Now, because C2 completes at time 3 and at that time C1 is not C1 has not finished. So, message M1 is not ready at time 3. So, at time 3 message M1 is not ready. So, the only ready message is M2, and that can be transmitted over the bus, and it is received at P3 at time 4 Okay. When this one is received at time 4, so two things happen at time 4. C4 starts, because M2 has already been received, C4 can start at time 4, and C1 also completes at time 4. So, message M1 can be transmitted at time 4 over the bus. So, M1 is transmitted and completes its transmission at time 5, at which time C3 can start. C3 takes only 1 unit of time, and both of them complete at time 6. So, C4 which takes 2 units of time also complete at time 6, C3 which takes only 1 unit of time starting at time 5, it completes at time 6. Now, at time so after C4 completes at time 6, message M3 can be transmitted, and the whole transfer, this message, final message M3 completes its transmission at time 7. So, now we see that we have a case in which when the computation takes less time, the whole process, this whole process takes more time to complete, 8 time units. So, when C1 takes 3 time units to execute, the overall time required by the embedded system to complete this process is 8 time units. However, when C1 takes more time, when C1 takes less time to execute, the whole process takes 8 time units, which is more amount of time. When C1 takes when C1 takes more time, then the entire process takes less time to complete. So, when C1 takes 3 time units, the overall process completes in time 8 time units. When C1 takes 4 time units, the overall process taken is only 7 time units. Okay. So, this is an anomaly. Why? Because the total time increases when computation takes lower amount of time. Now, this shows that we need to carefully do the scheduling of both the tasks and the processing elements together to correctly analyze whether the given embedded system will meet its performance estimates, so for example, time estimates. Now, we are seeing that in order to do system level analysis, we have to consider delays due to possible contention and preemption across tasks. So, we have to take the case of contention on the bus for messages, contention on the processors for the execution of tasks. Now, in order to do all this analysis on contention, we need to have an idea of what amount of time a task is going to take. Now, this is not very easy to do again. So, therefore, we have to first try to estimate the execution time that will be taken by a single task. Now, what is a task? A task is a sequential piece of code. So, it is important to be able to analyze the worst case execution time of task, which is its upper bound on the execution time. Why is such worst case execution time estimation difficult? Because the program may have infinitely many inputs. For example, let us say an image processing program, it can take any image as input and it will process that image. So, the input data could be infinite, and depending on the depending on the input, the program can take different control path within its control flow graph. We have already studied control flow graph. Let us say flow chart, it can take different control paths in the flow chart of the program. So, therefore, and each such control path may end up taking a different amount of time. So, therefore, the program can take different amounts of time to complete depending on which control path is followed by it, and which control path is followed by it depends on the data that it takes. The execution time of the program also depends on the platform, as we just saw, and the platform, when we do the execution time analysis, the final platform may not already have been decided. Therefore, execution time estimation is something beyond simulation or execution based approaches. We need to do static timing analysis or static analysis of a program. So, in a system level or execution based approach, we run the program over various types of data and try to analyze what will be the upper bound on the execution time that this program can have. However, what we try to emphasize here is that such simulation and execution based approach may not be complete, may not be accurate. What we need is static analysis, which is followed in a lot of cases. So, we will see how static analysis for worst case execution time estimation of a program is done. In order to conduct static analysis, we have to first generate the control and data flow graph or the control flow graph of the program. We already have seen how this is done in software. We will just going to reiterate. Let us say we have a program sum equals to 0 for I equals to 0, I less than 10, I plus plus. If I percentage 2 equals to 0, then sum equals to sum plus I. If sum less than 0, break, return. Now, the control flow graph of this program will be as follows. The first two statements. So, again, what was a control flow graph? A control flow graph is a directed graph whose nodes are basic blocks and edges denote control transfer across basic blocks. We have already seen this. And what is a basic block? It is a maximal code fragment executed without branching or of control flow. And how do we obtain the control flow graph? It is here. So, control flow, we already know this. For this program, the control flow graph is this. The first two statements are in the same basic block, because it is a single sequential execution. There cannot be any branch in control. It has one entry point, and the next node has two entry points. So, this goes into a separate basic block, and likewise we see. So, this is the control flow graph corresponding to the program that we have here. Now, what is the essential idea? How does the static analysis, how is static analysis done? Static analysis, which is the worst case execution time estimation of programs here for our purpose here. How is that done? We first find the worst case execution time of basic blocks. After we have done that, we compose the worst case execution time of the basic blocks according to the edges of the CFG to calculate the worst case execution time of the overall program. And this uses an ILP based formulation. This typically uses an ILP based formulation, which we discuss next. So, in an ILP based formulation, we start with the control flow graph. We first analyze the execution time of each basic block. In calculating the execution time of each basic block, we assume that each statement takes 1 unit of time. So, 1 unit time for each statement. Although this assumption may not be very accurately true, but for our purposes, when we are estimating big computation times, each statement taking 1 unit of time is a reasonable estimate. So, we will assume that each instruction or each statement in the program takes 1 unit of time, and let Ci be the execution time of each basic block. Now, for our case here, we see that basic block 1 has 2 statements, and therefore, its execution takes 2 time units. If we see all the other basic blocks, all the other basic blocks, each of them has one statement each, and therefore, all the other basic blocks take one time unit. So, C1 takes 2 time units, C2 through C8 all take 1 time unit. And now, given the individual, so now what we have a situation where we know the execution time taken by each basic block. So, given the execution time of each basic block, we just need to find the number of executions of each basic blocks. How many times does each basic block execute in the worst case? So, if we know that, and we also know the time taken when each time it runs, we can find out the total execution time of the program. So, the total execution time of the program will be given by summation over C I into N I, where N I is the number of executions of basic block I and C I is the time taken for each execution of basic block I. So, summation C I N I is the total execution time of the program. So, time is given by this. And here we know that for our specific case, for our CFG, C1 takes 2 units of time. So, C1 is 2 and all other C1s are 1. So, this expression essentially gives us the total time that will be taken by the program, and this becomes the objective function in our ILP. So, our ILP is this one, and the worst case execution time for the program will be the one which maximizes this value. So, we maximize 2 n 1 plus n 2 plus n 3 up to n 8, this value, the maximum value that is possible. So, we have to find valuations, possible valuations for n 1, n 2, n 3, n 4, and for that value of these decision variables n 1 through n 8, for which the value of so n 1 through n 8, the number of times each basic block executes here are the decision variables, and we have to find valuations of those decision variables for which the time taken by the program is maximum. And after getting the decision variables, we need to have constraints on these decision variables. We need to have bounds on each of these n 1, n 2 up to n 8. To obtain these bounds, we will look at the edges, and in particular let E I j is the number of time control flows from node I to node j. So, E I j is the number of time control flows from node I to node j. For example, E 1 2 will be 1, because control flows from n 1 to n 2 from basic block 1 to basic block 2 only once. Now, we can say that what will be the number of times that a certain basic block will be executed. So, basic block I will be executed n I times. What is n I? The number of times that control flows into this basic block. Okay. So, this is given by this expression here. So, E j I tells me that how many times control flows from basic block j to basic block I. So, for all such j's, for all j's for which you have an edge for which you have an edge from j to I, if you sum that up, you will get the total number of times control flows into this basic block. For example, how many times does control flow into basic block 2? It is E 1 2 plus E 6 2. So, E 1 2 is this one, E 1 2 plus E 6 2. So, number of times control flows from 1 to 2 and number of times control flows from 6 to 2, these two together tell me what is the number of times that control can flow into basic block 2. And similarly, it will be the same as the number of times that control flows out of the basic block. So, the number of times the basic block is executed is also equal to the number of times control flows out of the basic block, and essentially this property will be used to generate the constraints. For example, for our case, the number of times control flows into this basic block 2 is equal to the number of times this basic block executes and is equal to the number of times these two branches are taken. Okay. So, E I J, where I is basic block I and J could be all other edges from I to J. So, there are two edges from, so you have E23 and E27. So here we can say that N1 is executed once and E12 is once. How many times is N2 executed? E62 plus E12 equals to N2 equals to E23 plus E27, as we told just here for this case. Similarly, we have for other cases as well. For example, for N3, if we see, what do we have for N3? Control comes to this block from 2. So, E23 equals to N3 equals to E34. There are two outgoing edges from this basic block, and therefore, it is N3 equals to E34 plus E35. Similarly, the other constraints. So, we can obtain all the other constraints, but can we get any constraints from it? Although we know that this nodes 1 and node 7, node 1 and node 7 will execute only once, and these are the only two ways in which we can constrain the number of times these nodes execute. However, we have loops inside it. If we do not give loop bounds, ultimately the worst case execution time is going to become infinity. So, therefore, it is essential to put bounds on the loop to have practical execution time estimates. Now, N1 and N7 attempts to bound the execution count, however, loop bounds are essential. Now, how can we obtain loop bounds? If we look at this, we will see that if I is less than 10, we take this one, or if otherwise we go outside the loop. So, we get inside the loop if only when I is less than 10 and I starts with 0. So, therefore, this loop can be executed at most 10 times. This loop will be executed at most 10 times. Hence, we can bound, we can say that at most for nodes N3, N4, N5, N6, all these nodes will be executed at most 10 times. Can we do better is a question. So, therefore, here there is only one loop bound constraint, E62 is less than equal to 10. E62 is less than equal to 10. So, we can say that N4 will be so N4 is less than equal to 10 here, and N5 equals to N6, N5 equals to N6, N6 plus 5 8 is less than equals to 11. So, N5 equals to N6 plus E5 8. N5 equals to N6 plus E5 8, okay, and that is less than equals to 11. If sum is less than equals to 0, once it will go out. Hence, this is the constraint. So, therefore, when we get these constraints, when we get these more tighter constraints, it is possible to get execution time estimates, bounds on execution time estimates, and one possible solution, one possible feasible solution to this is 54 time units by putting these values on the decision variables. However, tighter the execution time, tighter the bounds, tighter will be the estimation on the maximum. So, lower will the maximum become, tighter the constraints that we put. Now, for example, how can we do such tighter constraints? By infeasible path determination. Are there paths which are infeasible? For example, in this case, we can see that yes, whenever I is less than 10, you come here to this one. However, I have I percentage 2 equals to 0. So, I percentage 2 equals to 0, if I is of I executes 10 times, this can be taken at most 5 times, it cannot be taken more than 5 times, because I percentage 2 equals to 0 will not become true more than 5 times in a span of 10. So, we can say that a bound on N4 is actually 5 and not 10. Okay. So, by doing this we can have even tighter estimates through infeasible path exploitation. To take another example on infeasible path exploitation, let us say that we have this program. So, while something, if I greater than 0, then j equals to I, else j equals to 1 minus I. So, when I greater than 0, j becomes equals to I. Now, if j less than 0, then k equals to I and j equals to k on the other side, I equals to I plus 1, this it enters this loop. So, we see that path 2, 3, 5 and 6, this is infeasible. Why is this path infeasible? This cannot happen. Why can't this path happen? Because when I is greater than j, we say j equals to I. So, j is also greater than 0. So, if j is greater than 0, the path for j less than 0 equals to true, that cannot happen. So, this path can never be taken. So, we can say that this path 2, 3, 5, 6, this is infeasible. This information may be captured in the ILP as follows. Suppose we can say that n 3 plus n 5 is less than equal to the loop bound. Why? Because n 3, if n 3 executes, n 6, if basic block 3 executes, basic block 6 does not execute. If basic block 6 executes, basic block 3 does not execute. So, therefore, if you have a loop bound here, so n 3 plus n 6 number of times basic block 3 executes plus the number of times basic block 6 executes, this summation will be less than the loop bound. Another way to look at it is that through the flow constraints here, that E23 equals to E57. So, whenever this path is taken, that I greater than 0 is true, I greater than 0 is true, you make j equals to I. So, therefore, j becomes greater than 0. So, whenever 2 3 is taken, edge 5 7 will always be taken. So, E 2 3 or the number of times edge 2 3 is taken is equal to the number of times edge 5 7 is taken. So, this is how we can take infeasible path into consideration and make tighter constraints. So, we have seen that how to obtain execution time estimates of tasks. However, if we do not take the microarchitecture or the platform into consideration, such estimates may not become very realistic. Now, how can we take microarchitecture and what is the effect if we do not take microarchitecture into consideration? Let us take a very simple example. So, till now we have seen that the time taken by the program is summation Ci into Ni. Now, let us say that in this program there are 2 add instructions, and this instruction, this same add instruction executes twice. The first time this add instruction is executed, there is a cache miss, that time it is brought into cache, and the second time again when this add instruction is executed, we have a cache hit. Now, assume that the cache miss penalty, say the level 1 cache miss penalty is 10 cycles. Now, for the fetch you need 11 cycles, decode, execute and commit. If you have these stages of the pipeline, if you have such a pipeline set of pipeline stages, then for the case in which there is a cache miss for the add instruction, the total time taken will be 14 cycles, 1 plus 10 cycles for the cache miss. So, 11 cycles for fetching the data, okay, for fetching the instruction. We are considering an instruction cache for simplicity here, and then it takes 11 cycles, but 3 cycles for the other 3 pipeline stages, and the total time taken is 14 cycles. Now, if we have a cache hit, the same fetch takes only 1 cycle, because there is no cache miss, and the overall instruction can be completed within 4 cycles. So, we see that for even a simple instruction, if we do not take microarchitecture into consideration, we may have to consider an average for this cache miss penalty or worst case, and the execution time estimates have to be much more conservative. However, if we can accurately model microarchitecture, although not always possible, we can have the opportunity of tighter estimates. So, let us see how within our model we can within our ILP based strategy for execution time estimation, how we can incorporate cache behavior. Okay. So, let us say that a basic block BI is partitioned into NI memory blocks. So, we are considering here a simple instruction, direct mapped instruction cache. We are considering a direct mapped instruction cache. Yes. So, this we are doing for our simple case. So, in a direct mapped instruction cache, each block in memory can be stored only in a single cache line. So, corresponding to each block, it can be stored in only a single cache line, as opposed to set associative caches and fully associative caches, where there can be multiple options for putting a block in memory into a cache line. So, a basic block BI is partitioned into NI memory blocks BI1, BI2 up to BINI. So, these are parts of the basic block, right. So, a basic block has NI memory blocks, and a memory block is what instructions within the basic block that is mapped to the same I cache line. So, therefore, I will require so BI1, BI2, BINI are memory blocks, and each of them will be mapped to a single cache line. Let us consider this simple program here. For I equals to 0, I less than 10, I plus plus, if condition, then a set of statements S1 is executed, else another set of statements S2 is executed. And for that, our basic block is something like this: I equals to 0, I less than 100 or I less than 10, something, let us say this is 100. I less than 100, I have a condition. If this condition is true, I go to basic block 4, otherwise I go to basic block 5, we come to basic block 6, and this loop continues. So, basic block 1 I equals to 0, I less than 10, I less than 100, basic block 2, this condition is basic block 3. Okay. And let us say we have only two cache lines, the gray cache line, line 1, and the white cache line, line 0. So, these are the two cache lines we have. We also see that basic block 1 is mapped onto cache line 0, basic block 2 is mapped onto cache line 1, basic block 3 is mapped onto cache line 0. Basic block 4 has two parts. The first, it has two memory blocks rather. Basic block 4 it is the only basic block here which has more than one memory block. So, memory block, the first memory block of basic block 4 is in cache line 1. The second memory block of basic block 4 is in memory the second memory block of basic block 4 is in cache line 0. Okay. Again, cache the basic block 5 is mapped only to cache line 0, and basic block 6 again is mapped only to cache line 1. So, we see here that basic block 4 has two memory blocks. Let CMIJ be the total cache misses for memory block Bij. Okay. For memory block Bij, CMIJ is the total number of cache misses. What is CMIJ then? CMIJ is the number of cache misses for the jth memory block of basic block I. Okay. So, Bij is the jth memory block of basic block I. So, CMIJ is the cache misses with respect to the jth memory block of basic block I. CMP, let CMP be a constant for simplicity, CMP be a constant denoting cache miss penalty. So, we are considering average cache miss penalty, and for each such cache miss, the average penalty is CMP. Then the total execution time now becomes what? So, I had Ci into Ni previously. What was Ci into Ni? What is I here? I is basic block I. For the ith basic block, I have Ci is the execution time of the basic block, Ni is the number of times that basic block is executed. Now, each time the so what is the then for this basic block, what will be the cache misses? The cache misses will be corresponding to each memory block within this basic block. So, this basic block I has Ni memory blocks, and for each such memory block you have Cmij is the total number of cache misses. Cmij is the total number of cache misses. Okay. Over all the times this basic block executes, Cmij is the total number of cache misses, and for each cache miss the overhead in terms of time is Cmp. So, now the total time taken by the program will be given by this part which we have already seen, and this part due to cache misses. For each basic block, for the ith basic block, I go to j goes from 1 to Ni, all the memory blocks. For each memory block, how many cache misses? Cmij is the total number of cache misses. For each such cache miss, the penalty is Cmp. Hence, the total overhead for each memory block is Cmp into Cmij. For the entire basic block, it's summation over j Cmp into Cmij, and that gets added to the time. Now, here we see that Cmp is a constant, and therefore, Cmij becomes a variable, and therefore, this has to be constrained. We need to get constraints, bounds on Cmij. So, this is done here. This is done as follows. What we have to do to obtain a constraint on Cmij is to generate the cache conflict graphs for each cache line. Okay. As the name says, cache conflict graph says that what are the conflicting memory blocks for this cache, and this will be dependent on for a given cache line from where the data. So, which memory block replaces which block on this cache line? What is the different who uses this cache line? What are the sequence of memory blocks which uses this cache line? To get that, we need the cache conflict graph. So, here we see that basic block 1 1. So, memory block 1 1, from memory block 1 1 on cache line 0, we are considering cache line 0. For cache line 0, first memory block 1 1 executes in cache line 0. After that, memory block 3 1 executes in cache line 0. Then, depending on control, memory block 4 2 or memory block 5 1 can execute. After execution of 5 1, control goes back to 3 1. So, basic block 3 1 can be replaced. So, basic block 5 1 can be replaced by basic block 3 1 on the cache line. Similarly, basic block 4 2 can be replaced by memory block basic block 4 2 memory block 4 2 in cache line 0 can be replaced by memory block 3 1 on cache line 0. This is for the cache conflict graph corresponding to cache line 0. Similarly, for cache line 1, what do we see? Firstly, memory block 2 1 is in cache line 1. Okay. After that, either basic block 4 1 will remain in cache line 1 if this path is taken, or if this path is taken, then memory block 6 1 will replace basic block will replace memory block 2 1. After basic block 6 1 completes execution, then it will go back to basic block 2 1. So, the loop will go back, and then on cache line 0, if currently basic block 6 1 is in cache line 0, that may be replaced by if memory block 6 1 is in cache line 0, after this loop goes back, then memory block 2 1 can replace memory block 6 1. So, this is what this cache conflict graph tells me. Now, what it also tells me that what is the number of times a certain basic block executes, a certain basic block executes. So, Ni tells me the number of times a basic block executes. So, number of times a basic block executes is equal to the number of times you have control flows into the summation of the number of times control flows into a memory block in that basic block. Suppose if you consider, let us say basic block 3, and we are saying that basic block 3 has one memory block B31. So, basic block 3 has one memory block basic block 31, and we are saying that how many times this basic block can execute, the number of times there is a transfer of control on this cache conflict graph from this ij, from a memory block of basic block I to somebody else. So, what we are saying is that what Rij tells me how many times does a memory block of basic block I go out to somewhere else. For example, for this basic block 3.1, there are two edges from 3.1. So, one is basic block 4, one is memory block 4.2, then the other is memory block 5.1. So, summation of the number of times these two edges are taken is equal to the number of times this basic block is executed. So, Rij to uv tells me that for here R31 to R42 and R31 to R51. So, these are the two outgoing edges in this cache conflict graph. If you take the summation of this, you will get the number of times this basic block executes. Okay. And similarly, it is also equal to the number of times that flow comes into this basic block. So, from other basic blocks, say from B51 and B42 and B11, the control flows into B31. So, uv in this case is 11, 42 or 51 and Rij is B31. So, number of times there is an inflow into this memory block is equal to the number of times this basic block is executed. Now, when we want to find CMIJ or the cache miss related to a certain memory block of a basic block. So, what is the number of times there will be a cache miss for memory block J of basic block I? It will be the number of times there will be a conflict, between BUV and BIJ. So, is equal to the number of times RUV to RIJ occurs, and the number of times that this RUG to IJ. So, number of times this inflow is conflicting, meaning that what do we mean by conflicting? That the contents of UV will be replaced by the contents of IJ in the cache line. So, for cache line 0, let us say we are saying that B42 is conflicting with B31 if B31 replaces the contents of Bij, or rather the opposite, B42 replaces the contents of B31. So, why do we want to say this? We want to say this because whenever control comes back to B31, if you have no trace of the previous contents of B31, then there will be a lot of cache misses. Okay. So, when will that happen? When B42 or B51 will replace the previous contents of B31. So, again reiterating, let us say we are considering cache line 0. In cache line 0 currently you have contents of memory block B31. Now, after your control goes to B42 and B51, let us say the contents of cache line 0 is evicted by the contents of B42 and B51. So, the previous contents of B31 no more remains in cache line 0. Now, what happens when I go back to B31, the previous contents of B31 are not there, and hence you have a set of cache misses, and therefore, summation of the number of times when BUV conflicts Bij, the summation, the number of times this edge is taken for the conflict, you have Cmij. By using this, we can have a bound on the cache misses that can happen. Okay. So, this is how we have given an overview as to how cache behavior can be modeled and incorporated within the ILP for estimating the worst case execution time of the program. Okay. With this, we come to the end of this lecture.